This is the CityFam podcast, with recordings from the CityFam Computational Design Symposium held in New York City, October 29th to 30th, 2025.
Hey guys, I'm Ryan O'Hara. I am at a company called Alloy Enterprises, and I'm our VP of Business Development. Fancy title, I'm wearing a suit, but you know, it's great to be back here and amongst my engineering brethren and maybe even some former colleagues. I was in the Air Force for 20 years as a developmental engineer, working a lot of advanced technologies for the Air Force, composites, high temperature materials, and was able to stand up one of the first metal additive manufacturing labs for the Air Force. Spent some time at NTOP and a previous contract manufacturer in additive manufacturing. And I'm excited to be at Alloy as the idea of manufacturing evolves and also how we tie that to computational design. So thanks for having me, and happy to answer any questions after the talk. Okay, so at Alloy, we're here to talk, and I got a bit of a unique talk that's a little bit different. We're showing some amazing things in computational design, and one of the things that I've been in my career is that always been in the intersection of like what the realm of what's possible and then what we can actually make. And I'm excited to talk to you a little bit about how we're leveraging computational design, but there's been some great presentations, and I don't want to be mean to anybody, some complicated ways of doing things. And I'm going to talk about computational design from a real practical and simple standpoint, and as it meets reality, right? And so one of the things that we're focused on here is to deliver advanced cooling solutions, enabling unmatched performance and efficiency for basically cooling, right? And the idea here is that we're at the intersection of manufacturing and design. Okay, got it. Keeping the whole rhythm down here. So we were founded in 2020. We're a 50-person team. About 75% of us are engineers. And we're based in Burlington, Massachusetts, just outside of Boston. You're more than welcome to come by if you'd ever like to see the things in reality, but you'll see them here today too. And we basically own end-to-end design, manufacture, and delivery of parts for customers with thermal management requirements. So like everybody here, or a lot of people here, you guys are all smart engineers and doing great things. Well, sometimes people just have problems and they don't know how to solve them, and that's kind of where they come to us, especially on the thermal management side. And I think there's some tools that we'll talk about today that you guys are using every day that are causing some thermal management headaches for people in the industry. So specifically, I'm going to talk about thermal management with liquid cooling, and it's going to be single phase, and it's only going to be with a fluid. There's a bunch of ways to deal with thermal management, but we'll talk about why we're focused on liquid cooling. And the big one here is this is a NVIDIA Blackwell chip, B200. And for some folks, this is making my life easier in terms of emails and doing my homework and writing essays, maybe even some talk tracks for presentations, right? But this is a NVIDIA B200 chip, right? And it is powering the AI revolution that we're seeing today. Trouble is, it gets hot, right? And if you're a chip designer in NVIDIA, I'll share some personal thoughts. I think maybe the chip industry didn't really think about all the implications of putting a lot of transistors in a very tight space, right? So this chip is about a 50 millimeter by 50 millimeter package, right? And it can produce quite a lot of heat, and we're talking about thousands of watts. Right? So what we need to do to mitigate that heat is we need to cool it. And it turns out that liquid or air cooling isn't good enough anymore. And so now you have to use a product like what we manufacture. This is a cold plate. And that cold plate sits atop of the GPUs, right? And it turns out, so those get hot, that gets hot, and then we're seeing even some new designs at some new chip conferences where there's 8 of these in a single rack, right? And then you'll notice that one rack is part of a whole bunch of racks in here, and it's all getting really hot, right? And so, and we'll talk about how hot they're getting is we need to talk about this increasing demand. Right, so you're seeing like a 30% increase in compounded annual growth in terms of thermal design power, or what we call TDP, right? And so the chip manufacturers are trying to respond to this, and I would almost say that they're kind of late to the game a little bit, right? And so they're trying to produce parts that are, how do I deal with this thermal problem? And everybody's kind of scrambling to figure it out. And then more importantly, there's a whole ecosystem, not just NVIDIA, right? That there's the people that make the motherboards, there's the people that make the racks, there's the hyperscalers. All these people are having to deal with thermal management at different levels, right? And the key here is, remember we talked about that 50 millimeter by 50 millimeter package? So, today's market, 1200 watts. They're talking about next gen chips up into the 3600 watt category, right? So like, I'm old, I finished college in 2000, so I still had incandescent light bulbs, right? So there's a 100 watt light bulb, I think of those, and that's like 50 of them, all kind of like in one spot, this little tiny area, right? And just one light bulb could be pretty warm, right? And if you're a kid in elementary school, you had a little chicken coop, and one light bulb kept all the chicks hatching and growing, right? So now figure 50 of those in that small space, and then you multiply that by like 8 of those on a motherboard, and then a whole bunch in a rack. It becomes a big problem. All right. So one of the things that we do, we provide value in a couple different ways. And the key is, we talked about that end-to-end ownership, and we have basically a whole library of geometry, right, that we can put into a part, right, through the design. Then we can iterate on those parts. That would be our computational design piece, where we have some folks here. You can see we have end topology here. We also use a number of other tools to design, and those things are actively iterating. And then ultimately, we have fabrication, right? So when you can do the design, you can iterate, and then you can fabricate so that your process is optimized. That becomes an ideal situation. And I'll talk about some of our process and how we own the manufacturing side. So a couple of key things, though, is that for our data centers and from like a direct liquid cooling standpoint, we can provide thermal management with low pressure drop. And if you're not familiar with pressure drop, that is the, when you're passing fluid through a passageway, it kind of wants to slow down, right? And that slow down and that flow ends up in a lower pressure. And so if you have a pump, that means you have to have a bigger pump the more pressure drop you have. So if you can mitigate that, that's going to be an ideal situation, especially when you're in a space-constrained environment like a data center, right? And also in that regards, bigger pumps or smaller pumps in this case would actually save you a bunch of power, right? And then you start stacking up all these GPUs, that becomes an issue. The other piece here is like electronics and water generally don't mix, right? So we don't want those things to leak, so that's a big deal, and you'd be surprised how many of these liquid cold plates actually do leak. The other key here is we do cooling, not just in data centers, but in other industries like semiconductor tests, high energy lasers, etc. And oftentimes we have to operate in either a high pressure environment or a vacuum environment. And then the other piece here is that GPUs are just the start. So it turns out the GPU gets hot, and then, well, if you're going to have a GPU with all this throughput, now the memory modules are getting hot, and then all the other peripherals, it just becomes a cascading problem of things, right? And so Alloy is like kind of, we'll say lucky or well positioned that we have a capability that can help across the space there. So Alloy started in 2020, and the original idea was that we were kind of born out of the additive manufacturing space in Boston, right? And a number of our founders were in companies like Formlabs and other folks. And so the idea here was, though, is that additive manufacturing, specifically with lasers, is often very expensive, and especially in metals, right? And the whole idea was, how could we make a low-cost, scalable process that could actually deliver large quantities of parts, right? And the idea here is that you'll see in number one there, we have a surface prep, but the key here is that we have a coil of metal, in this case aluminum 6061, right? And we also have a copper 110. So 2 materials, and the whole idea is after we surface prep that, we go through a construct process. That's basically, we take that coil and we laser cut it. We also can apply an inhibition layer with basically a binder jet, where we can prevent parts from sticking together. And ultimately, we're going to stack those parts together. And we're going to put them in the third part of the process, which is called diffusion bonding. And we're going to produce that part by adding, in a controlled environment, heat and pressure to form a solid part. So much like limestone, you get sediment layers on the limestone, and over time, that heat and pressure forms, a limestone or rock, right? In this case, we're forming bonded aluminum. And then what's unique about that is that there's no filler materials. So in cold plates, previously Brazing is used, where you basically machine a part, and then you put a solder or some sort of different material together, and basically put it in an oven, vacuum brazing oven, and it forms a solid part where that filler material bonds to both sides. Well, we're doing this as a tonic layer, so there's no different materials in there, and often in brazed parts, they're prone to leaking, especially over lots of thermal cycles. Okay, and then finally we just do a heat treat for that part. For aluminum and copper, it's a little bit different. Okay. So manufacturing in the real world, so we have real parts. That's our, that looks like that's our surface prep, right? And then this is our construct machine, and we have bonding machines. So we have 5 production lines on the cutting side and the bonding side. So we have plenty of throughput to do thousands of parts that you would need for a data center. Okay, and we have a whole bunch of certs. So I'll get on to the fun stuff. That's all like boring kinds of things here. But the key here is that, you know, there's a bunch of talks here about AI leveraging for compute. And then, you know, some of the things that go in here is that we have heat basically and coming from all of these different parts inside of the data center, right? Or in the server rack. We have it on the GPUs. We mentioned previously the DIMMs. Now we're talking about interconnects for PCIe cards and all sorts of other stuff here. Solid state drives is another big one. Things that I didn't even know get hot, actually get hot, and it's a problem, right? Especially when they're in that space-constrained environment. Okay, great, my video is playing, so that was a big question mark. So another key here is once you take that pressure drop and heat mitigation, you talk about thermal resistance, and now we have lower pressure drop. And then the key here is that we're taking kind of this network or a vascular type structure. So this is a CT scan of one of our parts. It's actually this aluminum part that I have here. Happy to talk about that more. And then these are actually some sheets associated with the part. So it's just sheet metal, right? And then we have multiple layers with different types of geometry that we bring together, and that's where the diffusion bonding process happens to form the solid one. But what we can do with this layered approach is we can have different types of geometry of different sizes, and that's where our computational design comes in. Okay, so this is optimized for different length scales. And the other key, we're going to talk about 2 areas of computational design. We're going to talk about how we massively parallelize the flow, and then how we actually get it to high surface area geometry, which we call capillaries. So that's kind of this next slide of this aluminum part that I showed. And we kind of take a multi-tiered approach. If you look at this, no laser on this here, but in the center image there, we basically have a series of passages that form like a network together to bring flow in, right? And then the key is, you'd be surprised, as I learned, especially in the defense and industrial space where I focus on, we get a lot of parts that need thermal management, but they're basically, it's called gun drilling. They basically have a bunch of drilled holes, and it's a pretty crude way of manufacturing, but it's very cheap, but can often provide a lot of turbulence and different types of things in those intersections. So one of the things that we can do with by owning the design and manufacturing process is sometimes just making flow smooth, or your passageways smooth, right? Put a nice bend, put a nice flow, and that's going to reduce your pressure drop a lot, because your flow is going to be nice and laminar, right? And we'll talk about laminar flow here in a little bit. The other key here is that we have microchannels, and you'll see that, so at the top we're bringing flow in, and then as we get down we're getting smaller and smaller into that vascular structure, where we're getting these nice microchannels, right? And then so there we go. So a couple things that we have are microchannels or microcapillaries, right? And the idea here is that with our process, we just have laser cutting sheet metal. So if you've had any parts made, like, or really any kind of a, you know, Dwan's second half and a grill out after this, that's all sheet metal and it's laser cut. That's a pretty common thing, right? And so what we can do is we can actually just do single line curve cuts in our sheet metal to provide a microchannel. And depending on the material, for like aluminum, it's 180 microns is our min channel width, and for copper, it's about 50 microns, right? So we can make these ultra-fine passages where the flow can come through. But oftentimes when you have flow, especially in a narrow channel, it's going to want to slow down, right? So if I had a long microcapillary, that's going to cause a lot of pressure drop, right? In this scenario, we actually just want nice thin and short channels, right? And by bringing in that network of flow, we're massively paralyzing that. And you're going to produce something that looks a lot like this. So we basically are bringing the flow in, and instead of having long microchannels that might be 25, 50, 100 millimeters long, we basically have microchannels that are about 5 millimeters. And when we do that, we get a nice laminar flow over that part, right? And then, but we still get a lot of surface area. Okay. And then apparently I'm talking faster or slower than I thought. So the other thing here is that from a computational design, we showed a lot of fancy things, but oftentimes all I need to know is where's the heat, and I'm going to put as many microchannels as I possibly can in that space, right? And that would be like the first iteration, and then I might, depending on where my ins and go-outs are, I'm going to tailor those microchannels to maybe avoid hot spots or provide a little bit more density where maybe I'm not getting as much flow. Sometimes on the ins and outs, we don't get to control that, and so you're kind of have to deal with the cards that you're left, and that's where our real computational design it comes from, and we do some things there. And that's kind of where things like NTOP come in, where you can use spatially varying fields to generate from simulation, and you can modify the geometry there. And then you can use other tools like Siemens Flow EFD. We do that for the CFD side. Then we can even tie those things into like neural nets and other types of things to tailor that microchannel geometry. I think the key here is just for a reference to when you talk about microcapillaries, depending on the manufacturing process, and this is key where we own it, is that you can get different size microchannels. With our process, we can make it as small as possible, and then by parallelizing it, we get a lot of benefit from that. And this is just a good example of what we're doing on the dim cooling side, and I think that's it for me. So appreciate everybody's time. I'll be around all day and tomorrow.
To see the full recording of this and previous presentations, as well as information about future CityFam events,